weekend, and we are just hitting the halfway mark, so energy going. So this week is going to be slightly more theory heavy. And to start it off, we have Professor Sachdev from Harvard, who's going to tell us, spread out over 4 lectures, potential resolutions to many of the mysteries of these infamous high-temperature superconductors. And you've probably noticed Subir was one of the first ones to post his lecture notes at the beginning of the summer school. I'm hoping most of you have worked through it and have come fully prepared last week.
Yeah, great. There was an update yesterday or something. So please. All right. Thanks, Evangeline. It's great to be here. I think I don't know if I came here as a student, but I've been here as a lecturer many times. Wonderful school that Leo has set up. And yeah, feel free to interrupt. I understand people have been speaking up a lot. So let me just set the stage by reviewing things that I think have already been covered. I'll use slides for that. And then when I start the main topic of the first lecture, which is just a theory of spin liquids, I'll use the board. All right, so this is all motivated, of course, by the high temperature superconductors, the cuprates. So is my mic working okay? So this is YBCO. And as I'm sure you've heard, the most important property is this square lattice of copper oxygen atoms. And all of my lectures are going to be motivated by all the amazing phenomena that that this simple system displays. So of course, this was discovered, way back in 1986, and we're still working on it. But I would say, it's sort of like Fermat's last theorem. It may not be solved, but along the way, a lot of other things have been discovered which have had applications in all fields of physics. So that, in that sense, it's been a wonderful problem to be working on. I was a postdoc when this was discovered, so it was perfect for me. All right. And another obligatory slide, if you haven't seen this. So one of the remarkable things is that recently, YBCO magnets are being used. This is I don't know, some sort of artist sketch of YBCO cable, inside which there's presumably going to be fusion. This is a company in the Boston area that's trying to do this. And yeah, it's probably a long shot. I mean, I think the issue here is not so much the temperature. It's quite easy to cool to liquid nitrogen, but the damage that the radiation does to these materials. So there's a lot of work going on now to make the system less resistant to radiation damage. Anyway, this is a long shot, but I tell people, well, quantum computing is an even longer shot, and this will save the world. So God knows what quantum computing will do. All right, is that being recorded? Fine. All right, okay. So this is the famous phase diagram. I presume Steve probably showed it because Steve was one of the people who made this famous phase diagram. So this is the density of holes in the copper oxygen layers. This is temperature. And this is the famous D-wave superconductor with the high TC. So today, I'm not going to talk, well, I will talk about superconductivity. So the one region where we think we understand what's going on quite well, or 1 or 2 regions, is of course the higher doping region, where photoemission shows these. This is a measure of the Fermi surface. It's really just a circle around pi, but you often see it drawn centered around 0, 0. And if you did density functional theory on this material, this is pretty much what you'd get. There are some mysteries down here as you lower the temperature. I think Steve must have talked about that. I'm not going to go into that. But it's an ordinary metal in the sense that it obeys one of the most fundamental theorems of ordinary metals. Theorems are properties of ordinary metal, which is the Luttinger property. So, of course, the theory of metals began with Sommerfeld in 1927, where he just assumed they're free electrons. And it's until 1906 that worked almost everywhere. But a deep theorem was discovered by Luttinger in 1960 using kind of Green's function methodology. And people argue whether it's perturbative or not. I come down on the side, it is perturbative. And one simple way to state it is that the area enclosed by the Fermi surface, so this is in 2 dimensions, in 3 dimensions with the volume, is the same as that for free fermions with the same symmetry. So, if there's some broken symmetry like antiferromagnetism or a charge density wave, just take some Hamiltonian for free fermions which have the same broken symmetry. And just compute this, whatever is the size of the Fermi surface for all the electrons. And that's an invariant. As you turn up the strength of the interactions while keeping the density of the fermion the same, the volume enclosed by the Fermi surface will not change. Of course, this is all modulo 2 for spin-full electrons, because you could have a fill band, and a fill band, doesn't contribute any Fermi surface. But that's also a problem. This statement is still correct, because free fermions could also have a fill band. So, so this is the simplest way to remember it. Now, a big step forward was made by Oshikawa, who gave a very different argument for this Luttinger theorem. I mean, he gave the same result, but it was a very important step forward because, first of all, it was non-perturbative. And today we would say, although he didn't use the word, it's sort of an anomaly matching argument. And this is going to be really key to many of the things I'm going to talk about. I'm not actually going to go through this argument. Senthil talked about it. Great. Okay, wonderful. And point here is that once you have an anomaly matching argument, so the way it works is that you have some system and you compute a certain anomaly. You compute how it responds to inserting flux, and you get an answer. This is how it must respond. Then you make an assumption for the low energy theory and see how your low energy theory responds. And then you say that those two must be equal. So that's the anomaly matching argument. And if you assume that the low energy theory is just the Fermi surface, well, then you get Luttinger's theorem. But there can be other fancy things in the low energy limit, which have their own anomaly. And that's the tool we're going to use to find exotic metallic states, which I'm going to argue are also relevant for the cuprates. Okay. So the other limit that's well understood is the antiferromagnet. Now, this is an insulator. So the conductivity is essentially 0. And for our purposes, what's happening is that you have a square lattice of copper atoms. There's strong Coulomb repulsion between the copper atoms, so they are localized one electron per orbital on the copper sites. And then because of the so-called super exchange interaction, they've ordered antiferromagnetically. Okay. All right, so those are the two limits. So let's go back to the first limit. Yeah, okay. Anyway, we'll come to this later, in a while. Okay, let's go back to the ordinary metal and then ask, can we understand the onset of superconductivity over here? So the way you would do this is the so-called Paramagnon theory, which I think Andre covered a little bit. So let me just sketch the basic argument. So we start with some Hubbard model, single band Hubbard model, some on sigma. And then you have an on-site interaction. And I up, and I down. Now, so the dominant term, and this is a small perturbation, at half filling, you would be at the antiferromagnet, and you'd get the antiferromagnetic order. But now I want to be at some other filling, say out here, and I want to ask, well, if you did a theory of this kind of superconductivity, will you get? This calculation was actually done by Scalapino and collaborators before the discovery of ITC. But they did it on, I think, on a cubic lattice, and they also mentioned something about the square lattice. Nobody thought there'd be a square lattice. Anyway, but they made the right prediction that it'll be a D-wave superconductor. So how does that, so let me just kind of sketch that argument. So the way we proceed is you take this particular interaction and you decouple by a Hubbard-Stranovic transformation. So basically, which is schematic here because this is really not the topic of my lectures. So you can write this as some integral over some field, a vector field phi, exponential, and then there's a trace for the fermions of, again, I'll be very sketchy with the factors of 2 and so on, phi squared over u plus phi dot c dag I sigma c I e I. Okay, so the idea here is when you do the integral over phi, you get back this interaction. And it's certainly possible to arrange it. And this is, in fact, an exact transformation of Hubbard interaction. This is K here. I'm going to take the antiferromagnetic ordering wave vector just to make it easier to talk about long wavelength limit of pi, of phi. All right, so what you have now, and there's, of course, the H0 of the fermion is still there. Okay. So what you have now is the theory of, here you have theory of strongly, here you have theory of electrons to a spin 1 vector field, a magnet. So it's spin 1 because it has 3 components. It's a vector in spin. We call that the Paramagnon. Okay, so imagine that you have some kind of strongly interacting Fermi system, and for some reason, this Paramagnon field is acquiring long-range correlations, becoming important at low energies and long distances. Now that's exactly what happens in this then well-established helium-3. In helium-3, that's where the Paramagnon theory for conductivity has its origin, for fluidity in that case, where people found that it was the ferromagnetic fluctuations of helium-3 that became very strong, and that led to pairing. In that case, because it's ferromagnetic, it led to triplet pairing, spin 1. So we take that same theory, which today people are busily applying to the twisted ballet materials. Somebody, and we apply it to the cuprates. So the only real difference to all of these other calculations is one, the geometry of the Fermi surface. It's on square lattice and it's a simple circle. And second, the Paramagnon is anti-ferromagnetic, not ferromagnetic. Okay, so that's pretty much all there is to it. So then you get this Paramagnon field. So you get this phi, which I'll represent by some wavy line. It has various spin indices that follow from that Pauli matrix over there. And that's all, those are very important to get the right side of the ring interaction. And it has some propagator. And you imagine it's long wavelength. So just like in any Landau theory, there's some Q squared. There's some R, which is when R goes to 0, then you have the onset of antiferromagnetism. But there's also some what's called Landau damping. So what happens is that this Paramagnon field, because of that coupling, it can emit a particle-hole pair. So this gives, the Fermi surface here, this gives you dissipation. So this Paramagnon is not really an oscillator, it's like an overdamped oscillator, but it's going to decay into pair of particles and holes around the Fermi surface. So for antiferromagnetism, this is a simple behavior. It's some constant plus mod omega with some coefficient. So we put that over here. And so this is what's called Landau damping in this context. Okay, I'm sure Andre spent quite a bit of time on this, right? All right, so you have some low energy paramagnon, which is somewhat damp, which is a spin 1 object. And now you ask, well, what happens? You can put some couple G. I think that's what Andre probably called it. And then you ask, what happens when R becomes small or G becomes large? What happens? Okay, so there's been some amount of work on that, especially since the discovery of high TC. But first of all, everyone agrees the simplest thing that happens is exactly what's observed, which is you get D-wave superconductivity. So, yeah, we'll come to this a bit later. But before I get to the fluctuations here, if I just consider the case here, R less than 0, so then, the phi field has got a negative mass. So that means you will go into a phase with phi is not equal to 0. So it's just a constant field. So now if you just take the Hamiltonian, H0 plus phi constant, and look at the surface. So I've broken the symmetry by the phi, and I just compute the Fermi surface. So when phi was 0, sorry, that could be phi, then you had this large Fermi surface I've showed you. And when you turn on the phi, it splits apart into electron and hole pockets initially, and then eventually into hole pockets. Now, these hole pockets are seen, the cuprates, at very, very low doping, where you do have long-range antiferromagnetic order, but the that I'm going to come to by next lecture is what's happening. Anyway, okay, so that's a bit of an aside. So this is the main thing I wanted to show you. So what happens, this is the BCS problem, okay? And so everything is in this picture. So imagine you have a Cooper pair of electrons, A and B. So here's A and there's B. Okay, so they're equal and opposite momenta, so that's your Cooper pair. So now this A interacts, this wavy line is the paramagnon. So as you notice from here, when you have that interaction between the electrons and the paramagnon, you change the momentum by pi pi. K is pi pi. So what happens to A, the electron at A, it gets a momentum kick of pi pi. It gets kicked to C. So A goes to C, and then B goes to D. So that's for pi pi here and pi pi here. So you really, it's a little bit more complicated in the usual BCS theory. You're mixing together different momenta. Okay, so Cooper pair at A and B will turn into a Cooper pair at C and D. And since twice pi pi is back to itself, then it keeps going. So Cooper pair at A and C, that's the Cooper pair here. And Cooper pair at B and D, you keep flipping back and forth in this propagation equation. Okay, so now this interaction, as we saw here, is strongly repulsive in general. So how come there's superconductivity? Well, it turns out that if you choose the pairing amplitude, the Cooper pair amplitude at this point and this point to have opposite signs, which they can, you're free to choose the sign of the pairing amplitude, then the interaction becomes attractive. So that's the essence of the argument. Other variations of the argument helium-3, which people were applying already to the heavy fermion compounds, and then also to the Hubbard model before the discovery of ITC. Okay, so that gives you then the D-wave pairing. The pairing on this region is the opposite of the pairing in that region, and that's what you see, okay? So you can see it really relies on the geometry of the Fermi surface and the fact that it's pi pi. if you apply the same argument to the pnictides, which have different geometries of Fermi surfaces, you can get all kinds of other pairings, S plus minus and extended S and so on. But it's just essentially the same argument. And also for the lots of papers applying this to graphene these days. Yes. Well, all right. Thank you. Okay. I skipped a step. It's 1 over u to begin with, correct. But we imagine that, well, let's see. Yeah, let's leave this here. Maybe I can write it over here. So we imagine integrate out the fermions a little bit. Then I will get the coefficient of phi squared will be 1 over u. And then let's call this g. Then order g squared, there'll be a minus g squared chi 0 plus mod omega if you want. And this is R. And chi 0 is just the zero momentum part of this bubble. Okay, so if you just, this self-energy graph that I drew over there, if you, at the integral, that just, if you assume that's just a constant, that just appears as a shift. Okay, thank you. Okay. So that's the Stoner theory of antiferromagnetism. When that Stoner thing you probably heard, right? U times the density of states gives you ferromagnetism. This is exactly the same argument, except this 0 is at momentum pi pi. So the part is the Stoner theory. This part is the Hertz theory. And then this, people did it. Yeah.
So here you connected by pi Parton.
Sure.
So what should we think about the pairing of the points that don't have an exact match with the pi?
Right. I mean, this is a schematic where the pairing is largest. I mean, you have to solve equation you have to solve where this has arbitrary momenta, and you have to integrate over these momenta, and also these have arbitrary momenta. This is where I'm just focusing on the points where it's largest. So this gives you the result that delta has opposite signs. Now, delta is going to be some smooth function around the Fermi surface, so it has to go through 0. So it'll go to 0 somewhere in between along the diagonal. That's where it goes to 0. And that's where you get no pairing along the diagonals. But that's just imposed by the fact that delta has to change sign where the pairing is strongest. There's no particular benefit in having a 0, but you're kind of required to have it. Yeah.
I realize your lectures are for helium 3, but the context in which Andre mentioned it,
Yes.
about Luttinger superconductor.
Yeah.
And if you just take vanilla cone Luttinger and do it for L equals 1, you get something. You get a TC that's comparable to the actual helium 3 TC.
Yeah.
That story is not secretly the same as ferromagnetic magnons.
I mean, Cole-Luttinger is just, I think, going beyond this one loop approximation, actually, adding more corrections to this. Okay, in some broad sense, it's very similar. I mean, Cole-Luttinger pointed out that there's always some channel that this is attractive. Here, I'm just, for the case of antiferromagnetism, it's just very easy to see that there's a wave channel.
The ferromagnetic channel didn't seem to have a special place.
No. I mean, Luttinger were motivated by helium 3, or yeah, I think so. So they were thinking you could certainly the Luttinger arguments to other momenta. Yeah. Okay, Andre is the expert on that. Yeah.
So here the antiferromagnetic order has condensed, right? It's fluctuation around the antiferromagnetic.
Well, this one, yes. But over here, I momentarily condensed it in the previous slide. Thank you. Here I condensed it, but here I haven't. Thank you. Yeah. If you try to apply this in the antiferromagnetic phase, that's very complicated. I think maybe Andre talked. Yeah, it's not as simple, the argument.
And is there anything studying the density in this picture between dxy and dx squared minus y squared?
Yeah,
The node like on the horizontal and vertical lines?
well, I think that that's if you take this particular Fermi surface and with pi, then you always get dx squared minus y squared. It could be different shape Fermi surfaces or different ordering wave vectors. I think if you had pi 0 ordering, you might get dxy. But for pi ordering and just a simple circular Fermi surface, you get dx squared minus y squared.
If I take your picture and I just flip it, so you mark A, B, C, D.
Yeah.
If I flip the sign of the 4 other points, then it's practically
Well, first of all, the sign of what?
other points that you didn't give.
In between here. Yeah. Well, I think you'll have difficulty connecting them with pi. Yeah.
Just like flip the sign of the order pattern.
Yeah, I don't know. Actually, you're right. If it's a perfect circle, then how do I know it's square? Yeah, so in fact, it is not exactly a perfect circle. Yeah, you're right. You're right. Thank you. Great. Okay. All right, so that's it for now. So let's go back to the phase diagram. All right, so this argument I presented, as I said, seems to work here. And okay, well, so one solution would be, well, just crank up the coupling and then you can get high TC. Nothing intrinsically wrong with that. The theory seems to be pretty well behaved, at least on its own. So what fails is not so much the theory of the superconductivity, but the theory of the metal. That if the state we're starting with, so this whole assumption is that we are starting with the Luttinger volume Fermi surface of well quasi-particles. That's the underlying assumption in every PCS calculation. But that fails completely. So even though the state here, I believe, there's no evidence that the state here is any different qualitatively from a BCS state, there's a lot of evidence that the metal above TC is completely different from a Luttinger metal. And that's, in some sense, the heart. So the first step would be to understand the metal before you really try to understand the superconductivity. And that will be the focus of at least my first 2 lectures. All right. So what happens in particular, well, the strange metal I'll come to in my last lecture. There you do see the same big Fermi surface, but it becomes very broad, very fuzzy. But it's much more dramatic in the pseudogap. That's really what I'm going to talk about. And I won't show you the pseudogap Fermi surface yet. We'll get to it in more detail than you care to know. But the idea, is that this pseudogap involves some very different physics that's simply not present, at least as formulated, in this theory of electrons interacting with a spin 1 Paramagnon. Okay. I believe, and I think most people are starting to believe anyway. I think Andre also agrees with me now. So Andre, in fact, in particular, to his credit, has done some very careful calculations, starting from this side, and then turning up the coupling and see if you get anything like the pseudogap. Now, that particular theory turns out to work quite well in the electron-doped cuprates. And the difference in the electron-doped cuprates, this magnetism goes all the way up to here. And so if your magnetism is up to here and you go above it, you can use this kind of theory. And it's been quite successful. But Andre has pretty much concluded that it's very, very difficult, although he's still trying, to make this kind of Paramagnon theory work all the way and first of all give you a pseudogap phase. Okay, so what I'm going to present is another idea that's also been around for a long time, but I think we now are able to apply it in a much more systematic way, which is that you need something highly non-perturbative to understand the pseudogap. And the key, one way to say it, which I'll now talk about, is that this must fractionalize. into S equals 1/2, not just the phi, but other things also all fractionalized. So we have to learn fractionalization. It's not something you will see by any of all orders expansion in this theory. It's a non-perturbative, it's a new phase of matter where you have to really start with a different assumption at very low energies. And that's really what I want to show you, how that's done. Yes.
So when you make it work,
Yeah.
whether all dope or electron dope, the theory is the same. It's the phenomenology and the experiments that is very different on the whole side and then the electrons.
Yeah, I mean, the primary difference between the electron on hole doped is the second neighbor hopping. So,
Even not taking home experiment.
yes. So to get this Fermi surface, you do need second neighbor hopping. You won't get that shape without the second neighbor hopping. It's not that small. So there's a hop. Here's your square lattice. There's a nearest neighbor hopping T1, and there's hopping T2. And I think T2 is around minus 0.3 T1. Well, no, that's the number. It's the same on both sides, the same Hamiltonian. It's the same Hamiltonian. T2 is minus 0.3. Yeah, that's the value of T2.
The phenomenology is.
Well, so let me tell you what that induces a difference. So when T2 is 0, then there's a particle hole symmetry. Then 1 plus x density is the same as 1 minus x density. You can just map the two Hamiltonians to each other by particle transformation. But when T2 is not 0, you can't. So if you take 1 plus x density with T2 negative, you will get 1 minus x density with T2 positive. So it maps onto a different problem. So the cuprates have T2 negative, period. And that tells you that 1 plus x is different from 1 minus x. Okay. So that's the most obvious, the biggest difference between the two. It's the same value of T2. The fact that T2 is negative destroys particle hole symmetry. Yeah.
Maybe a related question.
Yeah.
I'm not sure if you're going very microscopic, but like, can you see what is it about the sign of T2 that favors fractalization on one side and doesn't on the other?
Well, I think if you try to do this kind of first theory more carefully, you find firstly that the peak at pi is strong. So what it favors on the electron dope side is stronger antiferromagnetic order. Okay. Now, so the whole dope side seems to has the same antiferromagnetism at P equals 0, but once you add the holes, the antiferromagnetism is very stable, as strong as stability to antiferromagnetism. So at low temperature, you get stripes and all kinds of much stronger instabilities. And at higher temperatures, you get this pseudogap phase. Okay. So that, I'll talk about this a bit later, but I want to focus on, it's actually quite simpler to focus on this. So there is no clear pseudogap phase. I haven't defined what it is and what they observe. We'll do that next time. But there is, as you can see from this picture, everyone agrees, all these people have been arguing with each other for decades, all agree that there is something very special. There's a pseudogap phase, and it's well above any kind of ordering. You might see charge density wave ordering or superconductivity. The onset temperatures where you see any appreciable experimental, it's about 150 Kelvin. The pseudogap goes well above 300 Kelvin. That's still a relative temperature, okay? The J is, 1,300, 1,600 Kelvin. So when I say high temperature, that's relatively low. In fact, the cold atom experiments on the Hubbard model are actually even higher. They haven't come anywhere to this temperature yet. I think Marcus Klein is starting to reach that temperature now.
Can't attribute it, it's really a formula. You're just at high energy, so you can't really.
Yeah. So, right. So there's one point of view, which I think Kibelson has taken in the past, but I think he's been very careful about his claims, as you can see in this phase diagram. So one point of view is that there's some multiple. There's some multiple fluctuations of superconductivity, charge density waves. Even I've written papers on that stuff. And this is what leads to the pseudogap. But it's clear even from this picture that can't be the full story. Another point of view, which I've taken probably very strongly over the years, that the pseudogap, is a zero temperature phase. That in some universe, the hope is, or even maybe in our universe, pseudogap would be stable somewhere at zero temperature. Then, we can celebrate because then we can really study it as a quantum phase. And that doesn't seem to be the case in the cuprates, unfortunately. And in fact, I'll propose a model for the pseudogap, which is some kind of almost stable quantum phase. It has an intrinsic, and so thought that was a bug, but it's going to turn out to be a very important feature. So you do have to put in thermal fluctuations, and yeah, I may say about that. Yeah.
From Kibbleton.
Yes.
What he thing that was stressed in his lectures was that what's surprising about the underdoped side is the big difference between a gap that you find from the slope near the node.
Yeah.
Some temperature scale that you might extract still.
Yeah.
The latter determining TC on the other side. That kind of distinction not exist on the in the whole cuprate, in the electron doped cuprates?
The electron doped. I don't think there's been such a careful analysis, but there's clearly no such. If there's a pseudogap regime, it's very narrow, and it's just above where there's ordering. The ordering is much stronger.
Well, I guess these are questions that one would ask in the superconduction stuff.
Yeah, well, there may well be something exotic about this electron doped. In fact, I believe there's some regimes where that does happen, but let's stick to the whole doped. I think it's more complicated there. The pseudogap, I think people are arguing, is there a pseudogap, which is quantum rather than classical? There's any argument? Yeah.
Two brief questions. One, you're talking about zero temperature phases. Do we know you have this PC2
Yeah.
in this very qualitative picture, pseudogap possibly reaches? Do we have any idea from experiment that the region that isn't a charge density wave and is seen pseudogap down for low temperatures?
All right. So one thing I should mention is that this PC1 and PC2 is measured in high magnetic fields. So you add another axis, and you get rid of the superconductivity, and then you see some order. So then the question is, in high magnetic field, is there any region where you see kind of a pseudogap, but no order? There is a very tiny region in LNSCO. I was just talking to Louis Taillefer about it. So they've been studying it a lot. So far, what they hope to do, the key tool here is quantum oscillations. They haven't seen quantum oscillations there yet, but maybe, yes. Yeah, you can't, so in YBCO, which is the best material you can't even get rid of the superconductivity because the fields are way too high. But in FCO, which is a tertiary material, you can. So that's what makes the problem very difficult and source of never-ending arguments. Yeah.
Just very briefly, on the overdoped side, I would assume the mass of this Paramagnon is quite large. I'm very far away from the order.
Yeah, well,
that still works.
Well, that would work for the electron doped, right? So the mass, R goes to 0 when you hit this point in this simple theory. So can I use it over here? Well, I would say there are measurements of the Paramagnon in neutron scattering, and they clearly see antiferromagnetic dominance. But what they see is actually very, very broad. So in fact, the interpretation in our favor is what they're seeing over here, where they're seeing these very broad but intense Paramagnons, that it's really the signal of these spin half excitations. That's what, and there is no Paramagnon at all. Well, at least up to here. Over there, well, yeah, I don't know. But I think that's an important frontier, is to do a quantitative understanding of the neutron scattering to figure out where the Paramagnon theory works and where it doesn't. Okay, so the topic of my lecture today, which is briefly mentioned down here. So already after the discovery of ITC, Anderson said, okay, these are my words, but anyway, the key to high temperature superconductivity is something he called a resonating valence bond state. Today we'd call a quantum spin liquid. He was thinking in terms of quantum spin liquid with an energy gap, so the picture was, well, at that time, 87, we didn't even know there was antiferromagnetic order. So he was hoping that even in the insulator, there is this RVB state. That's clearly not the case. But it's still, I think, the correct idea, because building on the idea, which is what I'm going to do, we in fact is the key to understanding the pseudogap. So once you dope it, the correct reference insulating state turns out to be some type of spin liquid. Now, this was in 1987. We didn't even know what a spin liquid was. There was only one wave function. That's it. But that's a field now. This is a whole fancy field that has impacted quantum information, mathematics. There's something called unitary modular tensor categories, which classify in different types of spin liquids in the energy gap. So that's one of the things that people have been working on for the past 30 plus years. But it turns out that I think the relevant spin liquid is actually a gapless one. So that's even more complicated. And on that, there's been some remarkable progress in the last 5-10 years, which I'm going to now talk about. Okay. So let me now define the spin liquid a little bit better. What is a spin liquid, at least on the ones with this energy gap? The key is really exactly what I said there, that there's fractionalization. All right, so this is on the triangle lattice where, okay, at least on maybe the Kagome, this kind of spin liquid is known to exist today. So if we take the triangle lattice, then it has this kind of 120-degree order where you have antiferromagnetism. This is the classical ground state. It is also the quantum ground state for spin a half. That's known today, but imagine you can put in some second order coupling, and then can we get a resonating valence bond state? So this is the resonating valence bond state where the spins form singlets. And here's one particular pairing of the electrons into singlets, up, down, minus, down, up. And the actual wave function is a superposition of the exponentially many ways. This is e to the 10 to the 23 many ways that you can combine these electrons into singlets. So the number of dimer covering. So that's kind of the big wave function. So this is really the first wave function as far as I know. It's actually written down by Pauling before Anderson. But today, this is the first wave function that has what we call long-range entanglement. But despite being such a new kind of wave function with long-range entanglement, it's still quite subtle to experimentally detect this entanglement. It's not something you can just go in and measure. Yes?
To be clear, here all the valence bond are nearest.
Well, that's for this picture, yeah.
And
Yeah, these pictures are still very useful. Yeah, okay. This is not how we talk about these things anyway today. I'm going to discuss it using Parton theories and gauge theories, but this is just to give you some picture to keep in your mind of what these Parton theories are doing. Yeah, sure, they can be. I mean, these states are not even orthogonal, so this is all very crude. Anyway, so yeah, so there's a problem defining what exactly we're doing. And look at the bizarre topological order, but I've stopped using that word because the word topology now means something else entirely. And there's all kinds of fancy properties, and you put them in a torus and so on. But I think, to me, you ask, what is really different? What's really different? So different is the following. That if you now look at the excitations of this many-body state, they are local excitations, but they cannot be created by local operators. That's the key thing. So if you take any state you've dealt with before, PCS, Fermi liquid, magnet, anything, that is not the case. So what's about this case is there are required a non-local operator to create a local excitations. So you can then divide up the whole spectrum into what are called super selection or anyon sectors. And within any, you can go from any state in one sector to any state in the other sector by local operation. So those all states are, as far as the mathematicians are concerned, the same. They could have very different physical properties, but for the mathematicians, the Hamiltonian is 0, and so they're all the same. But then there's another sector where they're all the same to each other, but they all cannot be reached from this sector to this sector by any local operation. And then furthermore, now you can talk about, so I'm talking about an infinite system. But now you can imagine a system that is 2 times infinity, or 3 times infinity, and I've got 2 of these sectors here, one here and one here, and you move one around the other. Then all kinds of strange things can happen, and this is what the kind of thing that very beautifully classified by mathematicians. But the key is the existence of these sectors. So what is the sector here? The simplest example is exactly what I just said. So if I take this state and I apply some local operation. Now any local operation, like a spin flip, if I hit it with a neutron or X-ray or anything, in the Hilbert space of this spin system, the only thing it can do is change the local spin by 1. SZ is 1, because any operation that I have in front of me is a spin 1 object. So maybe I get this state. Okay, but now I can imagine, now I do a non-local operation. My non-local operation moves this guy out to infinity. All right, so that's gone. And now I have a state, which we call a spin-on state, which is a perfectly good state. It has an energy, this spin-on can move around. You can ask what's its dispersion. It could be gapless, it could be gapful, and so on. But it carries, as it moves around, it carries spin 1/2 and no charge. So it's got some exotic quantum numbers that no other particle before had, spin 1/2 and no charge. The electron is spin 1/2 and 1 charge. And it cannot be created, move the other one away. Okay, so this is the key object whose dynamics I have to look at, and related objects, so you can get many other, so if you want to understand a spin liquid with a gap, you would say, give me the super selection sectors. That's step 1, and then there's fusion rules and so on. So here, for the simplest spin liquid, which is called a Z2 spin liquid, there are 4 such sectors, which then appear later in the toric code. I'm sure all you know. There's a trivial sector, which is the ground state. There's a spin-on sector. There's something called the Vizon sector. I don't know, maybe Senthil talked about it. The name Vizon, you can blame Senthil for it. And then there's the bound state of a spin-on and a Vizon, which is another spin-on. I'm not going to talk about any of that, but so the theory of that is now well established. And certainly for a while, I wrote papers hoping that this kind of very simple spin liquid, which is closest to Anderson's vision, is the explanation of the supergap. Okay, there may be some truth to it today, but I've given up on that mainly because experimentally, that's simply not supported. But I'll present something else, which is, yes. Yes.
Going to see like some of these pictures, the fact that this is gapped and the spin doesn't have like nothing surface on it.
So I think intuitively you would say, since these are short-range bonds related to the previous question, if they were longer range bonds with power law decay, then it's hard to see from these pictures what it is. You have no idea. But if it's very short range, then then you can write down some effective Hamiltonian on this sector, which is called the quantum diamond model, and that you can see what the gap is, and you can even compute it in that kind of picture. Yeah.
Is this picture enough to say that this is like a Z2 gauge theory?
No. So this, yeah, so this, I mean, this picture Spinons, I don't know, Anderson or Bhaskaran or Kivelson came up with this. But a bit later in this paper that we pointed out, it's a Z2 gauge theory. There we were thinking about here to here, and we just did a very, this phase, we found that in addition to the spin-on, there had to be a Z2 gauge field and Wisons and so on. Yeah, so something I'm very proud of course. And all of this appeared later in the toric code, many years later. Yeah.
Could you say what you want to explain about the pseudogap?
Let's leave that for next lecture. I'll show you some slides on all kinds of properties of pseudogap. Okay, all of which I'll try to explain. Anyway, most of which. All right, so I think that's really it for the slides for today anyway. Right, so what I want to do today now is to talk about the analog of this picture for the square lattice. So this kind of Z2 spin liquid with very simple short range RBB type wave functions. If it works at all, it works on the triangular or Kagame lattice with strong frustration. But on the square lattice, there's zero evidence in any numerical work of a Z2 spin liquid. But there's a lot of evidence for a very different type of gap liquid, which is what I'm going to discuss. Okay. Any other questions on this general introduction? Yeah. Yeah. So the spin-on, this picture that I showed you, there's no local operator that can create an object which is spin a half and charge zero. There's nothing. You can't just create a spin a half on its own by any local operation. Okay. Sorry? Yeah. So the local operation created this object. You can create you just hit that singlet bond and convert it to triplet. That's a local operation. But then you have to do a non-local operation, where you move the other guy out to infinity. That's the non-local part. So the way, that actually gives me a chance to explain. So in fact, this is exactly, you can also see from here the need for a gauge field, why you need. So the object that creates this, I'm going to write down an object, the next, an operator that creates this guy. So that operator is not physical, it's not something I have access to. So in fact, and the reason, the way I impose that is that that operator will carry a gauge charge. There's some emergent gauge field, and that local operator that creates the spin-on must have a gauge charge. And so now, once you have a gauge charge, by Gauss's law, there must be an electric field operator. So in fact, that's kind of what I'm doing here. I create this object, and then it's the electric field, the flux. So that's how very naturally in emergent gauge fields, as long as you have an emergent gauge field and emergent gauge charges, you very much build up exactly this structure. And as far as I know, any fractionalized phase can be talked about that way. But okay, yeah.
But also implicit in this is that charge cannot move, right? Because this wave function is projected onto the charge.
That leads to certain constraints on the algebra of these operators, but no, I mean, this could be also be a Hubbard model. I mean, if I had a phase of a Hubbard model, it could even be a metallic phase. Could it have such sectors? I mean, that's still a fair question.
When you show this animation of
Yeah.
you could say, not like operator, but there's another operator. The charge was moving along with that spin.
Yeah, but then you would move a charge away. So then you leave some charge behind because everything has to be charge neutral, and this object would have charge and spin. That's fine, that's local. Question is, can you create an object with spin and no charge?
Right. What is it in this picture? It says that object doesn't have.
That's my statement, that's my claim. Even in some Hubbard model, I have a notation that I carry spin but no charge. that's possible, even in a Hubbard model.
In this Parton construction.
Oh, I mean, in general, yeah. People will extend the Parton construction, even systems with charge fluctuation. That's in fact the topic of my lectures. Yeah.
So there was possibly separate out these two spin-ons further away without costing any energy.
Yeah, no, it could be that it costs energy and they're bound to each other. Then you're not in a fractionalized phase. Then you're back into the Paramagnon theory. Yeah.
Operation neutron integrated these. What do you think is non-local operation? Is it?
Yeah, well, this people in quantum computing are working on very hard how to do all of this with gates. Yeah, that's an interesting object. In condensed matter, we don't really ask that question, but
Find neutrons when you measure a continuous
yeah,
light.
yeah. So you right to make predictions for neutron. Working on a paper on that just now. Okay. Yeah, sure. No, this is a question of energy momentum conservation. So if you have a paramagnon, which has some momentum k and some energy E, then it can split into two spin-ons. And this spin-on can have momentum q and some energy E of q, and momentum k minus q, and energy E of k plus q. Okay, now, all right, so what am I doing here? Yeah, so now, right, so now this energy has to be conserved. Now I'm getting very confused. EK. Well, no. So what this, it's not a paramagnon. You have some incoming neutron and it creates a pair of spin-ons. It has energy E and momentum A. So this E K minus Q. Okay. So now for each K, so when you're coming in, you're fixing your momentum K. So for each K, there's many possible choices of Q. And so the final energy, the energy of these things you're going to create has many energies. So you can scan the energy and you'll still see this process be active. So you'll get a very broad set of energies where it's possible to satisfy this equation. Okay, for each K, there's many energies for which you can satisfy this equation. So that's what's called the two spin-on continuum. Right. You can think of it as a paramagnon decaying into the spin-on, two spin-on continuum. Yeah.
So we are talking about paramagnon split fractionalizing into these
Yeah.
half particles, right? So what's the argument for that fractionalization? Like, why does it prefer fractionalizing?
Yeah, well, that's of course the big question. Yeah. So when Anderson proposed this, I said, yeah, show me an example. Now we have examples. Right. Well, I mean, this is what people have been doing all these amazing DMRG calculations to when it happens. I don't think we have a good understanding of when it's favored. Okay, let's get going. Yes. Sorry? No, these are two spin-ons. So forget. So this is a neutron. So you're doing neutron scattering experiment. You send in a neutron with energy K, momentum K, and energy E. And then you ask, is it going to absorb the energy? Now, if you had a paramagnon, if it's a very narrow, its energy E would have to be equal to the dispersion of the paramagnon. There'll be some very specific energy where you'll see a peak. You'll see a very sharp peak when this energy E is the energy of the paramagnon at momentum K. But now you have a more forgiving requirement. A neutron comes in, it creates two spin-ons. And so the total momentum is conserved, so the momentum of the neutron can be split into the momentum of the spin-ons in different ways. And each one of those ways will have a different. So in one case, if you had a Paramagnon as a function of k, if you looked at the, this is energy. If you looked at the intensity as a fixed momentum k, if you had a spin 1 particle, you'll see some very narrow peak. So this would be the energy of the Paramagnon, E of k or something. But with this, you're going to see some continuum. We'll see scattering where this is EQ plus E of k minus Q. So as Q varies, we'll get different energies. So if you can now properly interpret that whole thing. Now, so in one-dimensional spin chain, this works beautifully. You can interpret and actually iteratively compute the shape of that thing. So that's pretty conclusive evidence for the existence of spin-ons. And the hope is we can do the same in 2D. And in some triangular lattice compounds, this is, in the recent work, especially by Christian Batista and Joel Moore and others, it's starting to be realized. Cuprates, we're not there yet. Yeah, so the people who do quantum simulation with qubit devices, they can actually start braiding things and see, but their Hamiltonians are, very visual or 0 or something. But so they can have conclusive evidence of some kind of braiding properties, but we can't. We have to work with this.
And you see this continuum in the pseudogap?
You do, yeah. I'll show that eventually.
But sorry, this is also measured. So the metallic piece obviously has energy.
We're coming there. We're coming there. Hold on. This is. All right, so let me get to where I wanted to get to. All right, I haven't even started the lecture. I thought I'd have finished by now. All right, so what we're going to do, you can raise this, I think. So what I'm going to present is, I guess today we'd call Parton theories, the square lattice antiferromagnet. So there was a lot of work on this already in the 80s, early 90s. Then the subject kind of faded away. It seemed very confusing, none of which seemed to be any numerical work. But now I think things have come together in a very beautiful way. And we have a pretty good understanding of what spin liquids on the square lattice look like. Okay. So the Hamiltonian will imagine, just for simplicity, I'll just take nearest neighbor interactions on the square lattice of J. So here SI squared is 3/4. So it's a spin 1/2 object, and nearest neighbor, okay. This we know has long range Néel order, but let me just keep things simple. You can add further neighbor couplings if you want later on. And we want to think about possible spin liquid phases of this. Key defining property of a spin liquid is the existence of these spin-ons. So why don't we just go ahead and introduce them right away? So there's two ways to do it. Bosonic partons. And there's the fermionic partons. And both of them are in principle exact. So you might wonder which one should I choose? And different people obviously made different choices in the earlier days. So one choice is to write each spin operator. So I'll drop the index I, you can put it in later on. So on each site, you introduce a boson, which is two bosons, spin up and spin down boson, which carries spin 1/2. The hope is that eventually some linear combination of the boson will become Spinon. But this is just an example. Hilbert space on each side. Okay, so what go down? Each side I think of as a boson, the up boson acts on some. So what is the zero state? Zero is something, well, it's just some reference state that I introduce. It's not the vacuum of anything. It's just some unphysical state. And when I add a up boson to this unphysical state, I get the physical state. And then there's another state. There's only two states in my Hilbert space on each side. And so I have a constraint, B dagger up, B up, plus B dagger down, B down must equal 1. So either there should be up boson or down boson. And as long as this is satisfied, I only get physical states. So the Hilbert space of the bosons, these partons, is very large, but I only want to work with a subset of them. So it seems like a rather cool thing to do so many new states that are unphysical. The state with 10 bosons is just totally unphysical. It's allowed for the bosons in principle. But the point is that unlike the Paramagnon approach, it's at least allowing for Spinon to appear somewhere quite easily. Okay, so that's all right. And so these are canonical bosons. Otherwise, that also makes them easier to work with. They satisfy the commutation relation of canonical bosons. The spin operator doesn't. The spin operator has this very complicated commutation relation. You can check that this commutation relation implies this commutation relation. Okay, now exactly the same thing can also be done with fermions. You introduce two fermions on each side. Things damaging because there's the Pauli exclusion principle that helps you a little bit. And then you do the same thing. The up state is a fermion. And everything else is the same. F dagger up, F up, plus F dagger down. And these have the fermion anti-commutation relation, F alpha, F dagger beta, anti-commute. Okay, and these are both exact representations. All right, now, so which one should I choose? But try to don't. Then you go in and solve the problem, put the constraints, and you come up with some theory, and then you see. In some cases, maybe this theory agrees with the numerical data. Some cases, maybe this data. And then you conclude, this is what I should use because it agrees with this other much more complicated calculation that somebody did on their computer. And that's the case. What's taken many years to realize, and in this case for the square lattice, especially there's a beautiful paper by 2017, 2018 by Chong Wang, Adam Naum, Chinkeju, Senthil, and who's the fourth? Fifth, Max McLiskey, yes. 4 of them are students or postdocs of mine. But anyway, something remarkable happens. So they're both correct, and they both give you the same phase of matter. And so that, in some sense, implies there's some kind of there's dual descriptions of the low energy theory. which if you solved either description exactly, would give you the same answer. Of course, we can't solve either description exactly. And so the thing that I'm going to use is that for some questions, this is better. For some questions, that's better. And so we use the one so that gives you a lot of power. So we really have to learn both and understand the connection between them. And that's, of course, been the key to many advances in spin liquid theory. All right, so how do we proceed? Yes. It's not an electron because it doesn't carry an electromagnetic charge. It's, there's always one fermion present. So the electron operator we'll introduce later, this is not an electron, it's a fermionic spinon. It doesn't carry electromagnetic charge. It carries some emergent gauge charge that we're going to talk about right now.
The same definition, but you ended from different rotation relation.
Correct. Well, this is because these are fermions. The physical commutation relation is this. This is the same on both sides, of course. So you can check that you still have this commutation relation. So even though these anti-commute, these have the same commutation relation. This and this will both give you this and this. These are the same. Thank you. Yeah.
Physical left operator with a very large charge gap.
For now, let's not. You could. But then no. We will do that later. But for now, no. It's not an electron. Absolutely not an electron. It's just some fermionic object that must obey this constraint. Not allowed to change the number of fermions. Yeah, on each side. Yes. So at mean field level. Of course, if you could, if you're setting up a computer calculation, you could use the bosons on your computer, use the fermion, and you set up some matrix to diagonalize, you get the same answer. But when you do mean field theory, which is what I'm going to do now, you get totally different answers. So then that's what makes it confusing. And that confusion has slowly started to resolve now. Yeah.
Splitting a spin and expanding the degrees of freedom drifting into some physical space where it's vegan.
Yeah.
So it's complex program.
It's different. Yeah, absolutely, it's different. That's totally different. Yeah. Yeah. Right. What I'm trying to do is that the spinon, it took a very complicated object to really create the spinon. I am anticipating I can create the spinon in this construction because as far as this operator is concerned, at least on its own, it's unphysical. I can't add a boson on its own. But if I just look at the quantum numbers of the operators, it's exactly the right quantum numbers to be a spinon. So we want to understand how does this become a spinon at the low end in the final phase of the theory that we're studying. And it's not that hard. In fact, it works quite nicely. The hard part is then showing that your mean field theory is stable, because then this introduces a gauge field, and we have to then worry about what is the fate of that gauge field. Is it confining or not? That's really what the question becomes. So these are sort of like quarks. But the way particle physicists think of quantum chromodynamics, that they think of quarks as elementary particles, and which interact with some gauge fields. We're sort of doing the same thing here, but we are saying the spins are elementary particles, which are sort of the spins are analog to baryons and the mesons. And then we are right now on the theory where we're going to make the quarks emerge. Which is a point of view you could also take for particle physics in some way, maybe, that, quarks are deconfined at high energy, so Yeah, right. So these are emergent gauge fields rather than microscopic gauge field. But even that, in particle physics, people think of gauge field as somehow, God-given or something. But they could also be emergent as far as we know. It's more of a philosophical issue, I think. The difference is that the gauge couplings here are infinite, and in particle physics, they're not infinite. Yeah.
So rewrite these descriptions, right? So the distinction come in because does the gauge sector look different for bosonic versus the fermionic?
Yes, okay, let's talk about that. That is exactly the topic. All right, so first we're going to do is we're going to stick this. We're going to do something very simple. We're going to take this ansatz, put it in there, then I get some Hamiltonian with a 4 boson term here and a Hamiltonian 4 from there, and I just do Hartree-Fock BCS. That's all, okay? 15 minutes, yeah. All right, so again, let's be very schematic. You get all the factors of 2 and i's are in the notes. So you get B dagger I, BI, B dagger J, BJ here, and you just do Hartree-Fock, and then you pose the constraint by Lagrange multiplier. That's what you do in mean field theory. And then you get a H mean field, and you find the best mean field for the nearest. And in this case, it turns out the mean field is the following Hamiltonian, Qij, which is your mean field, B dagger I alpha, B dagger J beta, epsilon alpha beta, plus lambda. Okay. All right, so you get something like this. It's some quadratic Hamiltonian, and there's some self-sequence the values of Q and lambda, all right? They're all written down in the notes. So you just replace this by some Q bar and this by some lambda bar, and you just have a free boson Hamiltonian at the end. And there it is. Now you can declare, here's my Spinons. They have a Hamiltonian, they can move around, they have a dispersion. Let's go ahead and compute everything. And you get some dispersion here for the Spinons, which is EK, something like lambda squared. Right? Was it sine x plus sine ky? Okay, you get something like this. All right, so this thing has the property of it could turn negative, and then you have a square root of a negative number, which with bosons always means you're going to condense the bosons. So there's a phase transition. And so what you find, you can think of it in terms of varying lambda or some other parameter. So if lambda is greater than lambda c, you have a spin liquid. With bosonic spinons, whose mean field Hamiltonian is given here. This simple thing. And for lambda less than lambda c, the bosons will have to condense. So where will they condense? Well, they're going to condense at the moment where sine kx plus sine ky is the largest possible, because that's where this thing will first turn negative. So there's a very specific momenta at which the bosons condense. And when you've worked with that momenta, and then you compute the expectation value of S in this phase, you find is just e to the I k dot ri times some condensate, some b alpha squared roughly. So this is then the Néel state. So this is very exciting. This is one of the nice features of the boson state. It gives you the state that you actually observe. You get exactly the Néel state with all the right properties in terms of waves and everything when you do a careful theory of the fluctuations about the mean field theory. And then it also gives you a phase transition where you go away from the Néel state, where you have these potential gapped spin liquid with spin-ons of bosons. And this was the mean field theory that was worked out by Arovas and Auerbach in 1988. Yeah, everything there, they understood. All right, yeah. You don't. In fact, so yeah, all right. I will talk, that's what I wanted to lecture about, is what are the corrections to this mean field. The mean field has certainly a very nice feature. Yeah, maybe I will say something about it. I wanted to, yeah, let me talk, okay. I'll just talk about this mean field today. Tomorrow I'll turn to this one and how they reconcile. It's quite non-trivial. So here, as a function of some parameter, in practice, if you add a second neighbor coupling, this is what you get. So there's some phase transition here. And here you have the Néel state, where the spins are staggered. So this is B not equal to 0. Then there's a phase transition. Then here you have spin-ons with an energy gap. And they're bosonic spin-ons. Okay. And so they have this energy gap here. So because large enough, then this thing is always positive, and there's some momenta at which the spin-on energy doesn't go to 0. Actually, I have pictures of this. That's okay, I'll show it next time. Yeah, so there's some dispersion of the spin-ons, and you have this spin liquid state. Okay. So what we can make here, so there was an earlier theory of square lattice antiferromagnet due to Chakravarti, Happel, and Nelson. They took sort of like essentially the Paramagnon theory. They just took the Paramagnon theory of a spin 1 field. And then they said, well, just like I said earlier, there's some coupling R. When the R turns negative, you have the Néel state. And then when R is positive, there in the insulator, you have a gapped state. Now that gapped state in the Paramagnon theory has only spin 1 excitations, because it's just expressed in terms of Paramagnon. So Chakravarti, Happel, and Nelson have something they call the quantum disordered state, where you have no broken symmetry, G gap, and the only excitations are spin 1 Paramagnons. I mean, they're not magnons. Magnons tend to refer to spin waves. I guess we call them triplons today, because there's threefold degenerate, spin 1 triplons. Yeah.
The spin-on can be, so for the
Just the B. Just this B. So in this mean field theory, my unphysical B has become the physical spin-on, at least at this. Because, well, if B, but I don't have access to B. B is a fractionalized operator. I only have access to S. I don't have access to B. Yeah.
In the mean field Hamiltonian, is it supposed to be 2 B daggers in the first term?
Correct. Yes. Yeah. You need I mean, it's impossible for bosons to get a gap if you only had dispersion, and then they just always condense. You do need the pairing. Yeah. So it's sort of like a paired boson superfluid, but it's not really, because these are not physical boson. They are carrying. Yeah. So this is like a singlet bond operator. Yeah. So that's discussed in my notes. Thank you. Yeah. But what I was saying was that the Chakravarti, Happel, Nelson calculation, which at phase level gives a very similar phase diagram, where you've got a Néel and then a phase transition to something on excitations. And here we have almost the same thing. You have a transition from the Néel state to something which has no broken symmetry and energy gap, but it has spin 1/2 excitations. And now there's a theorem, which today we'd call that the, Lieb-Schultz-Mann-Hosting-Yoshikawa theorem. And the theorem is that it's sort of completely out of the Luttinger theorem. The theorem is that for any system, any spin system with at least a U1 global symmetry, it's impossible to have a trivial state with no broken symmetry. I don't know, there's no precise way of saying it, but that you cannot have but by trivial state, I mean something that's like where you can write on a very simple ground state, which is not entangled in any way. So the that's in paper is not correct once it goes into the quantum disordered regime. Such a phase is not possible for the square lattice antiferromagnet. Yeah, thank you. Right, but here, okay, here things are better. This is a non-trivial state. It's got spin-half excitations, at least allowed. It's a possible state. All right, but it's actually ultimately not that allowed because the mean field theory is not a very good mean field theory. So to really understand what's going on, we have to go back and think about this constraint a bit more. We can't just apply it at the mean field level. We have to fluctuations. You have to really think of the fold path integral of the theory and how you go beyond mean field theory. So the key here, actually also, well, for the boson it's simpler. The fermion is a bit more complicated. That this thing, this spin representation, and all physical states are invariant under a U1 gauge transformation. So there's a U1 gauge symmetry. Which is B I alpha goes to B I alpha e to the I phi I. So if I just rotate the phase of every boson by phase phi I, which can depend on space, can also depend on time, even if I'm doing a path integral, but let me not worry about that for now. Then this operator S remains invariant. And so this is a U1 gauge symmetry. And you can think of this as the sort of the, as the Gauss's law associated with this U1 gauge symmetry. This is just telling you that the total charge is always 1. So there's a background charge of 1, which is not allowed to fluctuate. And that's associated with this. So it's this sort of, you can think of it as another theorem. This is the symmetry, and this is the conservation on each side. All right, so the theory must have this U1 gauge invariance. Okay, so what's happened here for this mean field theory? Well, in the mean field theory, when we chose this kind of mean field ansatz to repair the bosons, introduced this Qij. And now you can see that the ansatz clearly doesn't respect the gauge invariance. The underlying theory had to have this U1 gauge symmetry. I made a mean field ansatz that breaks the gauge symmetry. Okay. Now, by itself, that's not such a horrible thing. We know that gauge symmetries, like in the theory of weak interaction, can break. Or in a superconductor, the U1 gauge symmetry breaks electromagnetic. So maybe that's all that's happening. We've broken the gauge symmetry, and so maybe you're safe. Yeah, okay. So let's just think about what the gauge symmetry is over here. I'm out of time. Okay.
I think we should go for 5 minutes.
Okay, all right, great. Yeah, so here, so under the same gauge transformation, Qij will go to Qij times e to the I phi I plus phi j. Okay, if you want to make this invariant, yeah, I got the sign right. Okay, all signs are right in my notes. Okay, so here's the gauge symmetry. So it seems like the moment you fix Q to something, then the gauge symmetry is broken. And just like in the theory of weak interaction, maybe there's some massive Higgs boson, which is bound state of 2 Spinons. But other than that, no worries, this is stable. Okay, well, it turns out for this particular nearest neighbor square lattice, that is not the whole story. And the reason is that there is a certain gate symmetry that is not broken, even by this ansatz. So if imagine now, here I have to remember that this I and j are on opposite sublattices. I'm only taking nearest neighbor. So in that case, if I take gate symmetry, where phi I is equal to, say, plus phi for I belonging to the A sublattice, and phi I is equal to minus phi for I belonging to the B sublattice, then the mean field theory, then Q bar, the mean field Q bar goes to Q bar. Because at least nearest neighbor, it's a bipartite lattice, and I'm only taking this Qij on nearest neighbor bonds. So in fact, there is an unbroken gauge symmetry. And associated with that, what we learn when we do the path integral of this theory, that there must be a photon. So there is in fact a photon, and the low energy theory is the theory of these bosons interacting with an emergent photon. So then you have to understand what is the fate of this theory of bosons interacting strongly with this emergent photon. I will stop here. I'll say a bit more about that tomorrow. I won't go into the details of that theory because it turns out to be a bit complicated. And then I'll turn to the fermions, where some things are simpler, some things are complicated, but we'll learn a lot from that. Okay.
Questions about that break paragraph?
Yeah. Okay, so numerically, which is I mean, if you do mean field theory, people have done quite sophisticated mean field theories, and they get quite similar answers. You have to do a better mean field theory than I've described here to take many more terms. But it's around 0.4. So experimentally, what you see, the 0.4 around, and then when J2 is really large, then you go into some other phase we're not interested in. But there's definitely what's called a valence bond solid. So what happens is that it's not like an RVB state, quite like an RVB state, but it's a state where the singlets kind of crystallize. The spins form singlets, and they crystallize, say, into some columnar pattern. Of course, they're resonating a bit, but they're also crystallized in this way. So there's 2 spin and a half in a cell, and there's a broken translational symmetry. So this is, in fact, the phase. Take theory and you add the U1 gauge field. Actually, I don't think I'll say much more about this because it's a big part of my life, but it is a rather complicated calculation. So if you do that calculation carefully, you find this symmetry is broken. It's not really a spin liquid, although ultimately at long distances, I mean, a short distance they might be spin-on. Ultimately, a long distance is the spin-ons pair up and confine. So that's what the U1 predicted and seen in lots of numerical works.
You studied the 2 spin here.
Yeah.
Like larger and sphere. What is the spin?
Yeah, so we've studied that also in great detail. In fact, it doesn't. There's a generic instability to the valence solid. It might a certain deconfined critical point, which I'll talk about next time.
That's a property of 2D, right?
Yes. Yeah, so this is related, exactly. So yeah, so this is a U1 gauge theory, and U1 gauge theory in 2 dimensions, 2 + 1 dimension, is always confining, similar to quantum chromodynamics in 3 + 1 dimensions. And because of that property, in fact, this A robust Auerbach spin liquid is never really stable.
You meant you want gauge to be without any energy matter. Spinon is this with the
Let's say gap theory with gap spinons. Yeah, thank you.
Question behind this Anderson comment of
Yeah,
the heights are
yeah. Yeah, that's a good question. So the intuition, I believe, was the following, that, what is our picture of superconductivity? A picture of superconductivity is you have some electrons, they attract each other, they pair, and they form pairs. Okay, so Anderson's intuition was, well, in the spin liquid, the electrons are already paired. It's just that they form singlets. And then if you could just make the singlets mobile, you get a superconductor. Okay, so I think initially he was even thinking of some exotic superconductor. I think that idea is correct, the pseudogap, but understanding how to implement it has taken 30 plus years for a good reason, because we now understand spin liquid is much, much better. But the state we get at the end, as far as we can tell, is just a PCS state. What's novel is that the mechanism, it's a different mechanism for the same state.
I guess it's a historical question. What's actually going on is gapless and different. But when people saw paramagnetism from neutron scattering,
Yeah.
what led people to be persistent in thinking about spin liquids? That it was some proximity in the phase diagram. Were people thinking there was a J2? We were just hopeful.
This is almost a religious question. There were those who loved Anderson, and they say, "Oh, it'll go away." I'm just joking. And they say, "Oh, finally Anderson wrong. Let's forget it." All right. The answer is somewhere in between, I think. No, but I think the point is that once, I would say for me, I started getting I was working on all of this stuff, but just for fun, it seemed like a fun problem to work on. I think it was going to solve the ITC problem. But I think, when the pseudogap started being clearly defined in so many experiments, these Fermi arcs and other things I'll talk about, those came out quite a bit later, 2000 plus. And I think there was definitely a revival of interest. So I'd say the MIT group continued anyway. And in some sense, they predicted the existence of pseudogap. So, yeah. But I think the pseudogap certainly has converted me much more of a believer of those ideas. Yeah.
Phi for all on out?
Well, so the Q bar is non-zero, and if I make this uniform, then the Hamiltonian goes back to itself. Yeah, good point. So it's a global symmetry. But now imagine I make it slowly varying. So if I make it slowly varying, then I'm going to get a very small change to the energy. And that'll be my gapless photon. Okay, so that's why first you consider global for the state that have no gauge fields. Then once you make it less than global, then you can introduce a gauge field to account for that very low energy. So it tells you there's some low energy mode. Yeah.
About the gauge stuff. So if you add the next nearest component, J2,
Yeah.
I think Qij is on the same sublattice.
Yeah, so then in fact the gauge symmetry is much simpler. It's just Z2. Then the phi has to be pi, only pi. And that's how, in fact, we got the first theory of a Z2 spin liquid. Yeah.
It's just an observation or comment that happened now. So
Yeah.
I mean, if you're trying to get magnetism, a natural way to decouple is to decouple decouple as a package S
Yeah.
times the Hubbard-Strange field.
Yeah.
Right? Magnetization.
Right.
While you're decoupling in the particle channel into singlets with integrated Hubbard-Strange fields, they both back this.
Correct. Yeah.
So
Yeah.
the different thing is that you're decoupling with a different Hubbard-Strange field.
Yes. Yeah. That's certainly a key difference.
Qualitative distinction.
Well, but more importantly, also, you can do theory in charge density wave, spin density wave, pair density wave, PCS channels. Those all don't have the feature that this does have, which is fractionalized particles, emergent gauge fields. So that, but it is certain decoupling that gives you, we are applying old tricks, but in a slightly different context.
Inside of how you
Yeah,
test that is.
yeah, yeah. Theory. And for the J1, J2 model, we found that the Q on the J2 bonds are always 0. Except it suddenly turned on beyond here where you got some other long range order. But for the whole range, it was just 0. But if you put the J1, J2, J3 model, then you get a Z2 spin liquid with bonds on. That's just a feature of the mean field theory. Ultimately, you need numerics, and numerics do show the kind of phase you would get from a U1 gauge theory.
So, could you elaborate more on why the uniform gauge choice is justified? Like, does that lower down the energy?
No. So the gauge. So what I'm doing is first I do Hartree-Fock BCS. I close my eyes and I open my Fedorov-Velechko or whatever, Mahon, and just do it for these bosons, and I find the best state. Okay, now I'm trying to think about fluctuations about this.
I see.
Okay, and analogous to when you're looking at getting Goldstone's theorem. If you broke symmetry in your mean field theory, that's fully energetic, you've broken it, you want to understand is there gapless spin waves, okay? And for that, you use the fact that your mean field theory doesn't change energy if you rotate all the spin by the same angle. And then that tells you that there has to be a Goldstone mode.
Yeah.
So this is exactly the analog of that, except that I'm not physically changing anything physical, I'm just changing the partons. So it seems like there's a certain change of the parton that doesn't change the energy. So then I ask, what happens when I change the parton slowly? What is is there a low energy mode? And in this case, instead of it will be a photon.
So it's basically the analog of spin wave to antiferromagnetism part on that.
Yes.
With that, let's